Hello students, I am Dr. Manisha Verma from Acharya Narendra Dev College, Delhi University. I am teaching physics there. Recently, I have started a lecture series on thermal physics. In my first lecture, I dealt with heat engines. Thereafter, I concentrated on real gases, wherein I introduced the concept of real gases, the various experiments performed to find out the features of real gases, what makes a real gas different from an ideal gas, is CO2 a real gas or is CO2 an ideal gas. I also discussed some very important experiments, Joule-Thomson experiment, Andrews experiment, Amagat's experiment, etc. in my previous lectures. Thereafter, I have begun my lecture series on Kinetic Theory of Gases. In my earlier lectures, I had discussed various assumptions of the kinetic theory of gases, how the assumptions helped us in deriving the various gas laws like Boyle's law, Dalton's law, Charles' law, etc. Thereafter, I have discussed what is the Maxwell's law of distribution of speeds, how to derive it from basic concepts, what is its importance in the kinetic theory of gases, how it can be used to find out various factors of kinetic theories of gases. So in continuation of my earlier lecture, let me now start from where I left off in my last lecture. In my last lecture, I had introduced to you what is the Maxwell's law of speed of velocity. Now, the most important thing about that law is that that law enables us to find out the average speed, the most probable speed, and the RMS speed of the gas molecules. Let me first distinguish between the three kinds of speed. What is the average speed? The average speed is the sum of the speeds of all the particles divided by the number of particles. What is the most probable speed? The most probable speed is the speed associated with the highest point in the Maxwell's distribution. Only a small fraction of particles might have the speed, but it is more likely than any other speed. This graph is showing the variation between the number of molecules with speed. The number of molecules is given by the Maxwell's law of distribution of speed. How it is varying is shown by this parabolic curve. As you can see, with speed, the number of molecules is increasing. It reaches a maximum and then it is showing a decrease with further increase in speed. So why are we getting this? Again, let me reiterate. The increase with small increase in V is because of the factor V square that is occurring in the Maxwell's law of distribution of speed. It reaches a maximum and then it starts showing a decrease. Why a decrease? Because the exponential factor in the Maxwell's law of distribution of speed contributes now, becomes more dominating, and then therefore the number of molecules start decreasing with large speeds. Now this graph is showing the point of occurrence of three speeds: the most probable speed, the average speed, and the root mean square speed. I will be shortly deriving all the expressions for these three speeds, but as you can see from the graph itself that Vrms is greater than average speed and average speed is greater than most probable speed. This means that the most probable speed is the smallest of the three. So let me now derive the three kinds of speed to bring out the difference between the three speeds. So the mean or the average velocity are called the C average. The average speed is the sum of all the velocities ranging from 0 to infinity divided by a total number of molecules n. Now, as you know, in my last lecture where I had discussed the assumptions of kinetic theory of gases, we had seen that the gas molecule can have any velocity. It can range from 0 to infinity. So, what we do is, to calculate C average, we take the integral of C into dn and divide it by the total number of molecules n. So, therefore, C average is 1 by n integral of C dn. Now, what is dn? dn is given by the expression from Maxwell's law of distribution of speed. So, let us substitute the value of dn in the above equation. So, C average becomes now 1 by n integral 4 pi n into m by 2 kt raised to the power 3 by 2 e minus mc square by 2 kt into c square dc into c. Now, this c which is occurring at the last of the equation is because we are calculating C average. Had we been calculating C square average, we would have multiplied by C square, as you will just see. So, this is the derivation of C average. So, C average can be written as 4 pi m by 2 pi kt 3 by 2. This is taken outside the integral sign because all these are constants. Integral of 0 to infinity e minus mc square by 2 kt c cube dc. So, c cube and c square are inside the integral. Let m by 2 kt be denoted by b. We have taken b as a constant because m is a constant, 2 is a constant, Boltzmann constant k is a constant, T is the temperature which is a constant. So, we replace all the three constants with a single constant b. The expression then takes the value C average is equal to 4 pi b by pi raised to the power 3 by 2 0 to infinity e minus bc square into c cube dc. Now, 0 to infinity e minus b square c cube dc, the integral of this expression is 1 by 2 b square, as everyone knows. So, C average becomes now 4 pi into b by pi raised to the power 3 by 2 into 1 by 2 b square. Simplifying this expression, we get C average is equal to root of 4 pi b. Therefore, C average will now become, after substituting the value of b, 4 by pi, b is m by 2 kt. So, simplifying, we get C average is equal to root of 8 kt by pi m. 8 is a constant, k is the Boltzmann constant, again a constant, pi is a constant. For a gas, m is a constant, T is the absolute temperature. So, basically C average depends upon T and m. M is the mass of gas molecules, of a single gas molecule. If we take capital M as the molecular weight, it can be written as m is equal to small m into Na. This means that small m is equal to m by Na. Here Na is the Avogadro's number. Therefore, the above equation will now become C average is equal to root 8 kt by pi m by Na. So, this is C average. Now, let us calculate root mean square velocity, which is represented by CRMS. First of all, students, you must understand what is meant by root mean square velocity. Root, mean and square. It means we take the square of velocities first take its mean and then take its under root. So this RMS speed is the square root of the sum of all the squared velocities ranging from 0 to infinity divided by total number of molecules, capital N. As told just a few minutes back, CRMS can then be written as root of integral of 0 to infinity dn into c square by n. N is the total number of gas molecules, c square is the square of the velocities of the molecules, dn is given by the Maxwell's law of distribution of speeds. Substituting the value of dn in the above equations, what do we get? We get CRMS is equal to root of integral of 0 to infinity 4 pi n m by 2 pi kt 3 by 2 e minus mc square 2 kt c square dc into c square divided by n. So mind you, while we were calculating C average, we had, instead of C square, we had C. Now because we are calculating C square average, so we have multiplied the expression by C square. Had we been calculating C cube, then we would have multiplied by C cube. N is the number of molecules. So simplifying and taking the constants outside the integral sign, we get CRMS is equal to root of 4 pi m by 2 pi kt 3 by 2 0 to infinity e minus mc square by 2 kt c to the power 4 dc. Why to the power 4? C square because of CRMS and 1 c square because of the Maxwell's law of distribution of speed. Again, m by 2 kt is denoted by b. So what do we get? We get CRMS is equal to root of 4 pi b by pi to the power 3 by 2 0 to infinity e minus bc square into c4 dc. So let us simplify the expression further. The value of the integral is 3 by 8 pi by b5 3 1 by 2. So simplifying, we get root of 3 by 2b. What is b? b is m by 2 kt. So substituting the value of b, we get CRMS is equal to root 3 kt by m. 3 is a constant, k is a constant, T is the absolute temperature, m is the mass of a single gas molecule. Next, let us calculate what is the most probable velocity. The most probable velocity is denoted by CPR. The most probable velocity is the velocity possessed by the maximum number of molecules. Now students, you must have read in your schools that whenever we have to calculate the maximum number of molecules, the rule is simple. We have to differentiate and equate to 0. Hence, to find out the most probable velocity, we take differential of dn by dc and then equate it to 0. So as written, d of dn by dc is equal to 0. dn is given by the Maxwell's law of distribution of speed. So what do we get? d by dc 4 pi n m by 2 pi kt raised to the power 3 by 2 e minus mc square by 2 kt c square dc equal to 0. So here we are differentiating with respect to c, that is with respect to the speed or the velocity. Now we can take the constants outside the differential sign. So what are the constants? The constants are 4 pi n, m by 2 pi kt, 3 by 2. So let me take them outside the differential sign. So what are we left with? 4 pi n, m by 2 pi kt to the power 3 by 2 d by dc into e minus mc square by 2 kt into c square dc equals to 0. This means we have to differentiate e minus mc square by 2 kt into c square. These are two terms. The first term is e minus mc square by 2 kt and the second term is c square. So we have to use now the product rule. As you can see, again outside the bracket we have 4 pi n, m by 2 pi kt, 3 by 2. The differential of the two terms is yielding two terms now because of product rule. So we have e minus mc square by 2 kt into 2c. 2c we are getting because of differentiating c square, and the second term is c square into minus 2 mc by 2 kt e minus mc square by 2 kt. Here, because of differentiating e minus mc square by 2 kt, we get minus 2 mc by 2 kt into e minus mc square by 2 kt. As told just earlier, after differentiating, to find out the maximum number, we have to equate to 0. So equating to 0. Simplifying the equation, we get 4 pi n, m by 2 pi kt to the power 3 by 2. Taking e minus mc square by 2 kt outside the bracket. So we get two terms in the bracket now, 2c minus mc cube by kt, which is equal to 0. The term outside the bracket, that is 4 pi n, m by 2 pi kt 3 by 2, e minus mc square by 2 kt becomes 0 on transposing it to the right hand side. So what are we left with? We are left with 2c minus mc cube by kt equals to 0. This means mc cube by kt is equal to 2c, or c square is equal to 2 kt by m. Therefore, c becomes 2 kt by m root of. This is the most probable velocity. 2 is a constant, K Boltzmann constant is a constant, T is the absolute temperature, m is the mass of single gas molecules. Substituting small m by capital M by Na, where capital M is the mass of the gas, Na is the Avogadro's number, what do we get? We get the simplified expression. Now let us find out the relation between most probable velocity, average velocity and the RMS velocity, how they are related to each other, which is the maximum. So here we have calculated the ratio between CPR, C average, C RMS. CPR is 2 RT by m root of, C average is root of 8 RT by pi m, C RMS is the root of 3 RT by m. So simplifying, we get root 2 is to root of 8 by pi is to root of 3. To simplify further, we get 1 is to 2 by root pi is to root 3 by 2. So just simplifying this further, we get 1 is to 1.128 is to 1.2 0.28. This shows that C RMS is the maximum and the C probable is the minimum. This is very interesting. Now let us illustrate the difference between these velocities by taking a very simple example. Let us consider an ideal gas with the following distribution of speeds. The mass is given as 3 into 10 to the power minus 26 kg. We have to calculate the RMS velocity and the temperature. Further, we have to calculate one more thing. If all the molecules with speed 1000 meter per second escape from the system, we have to calculate the new CRMS square and hence T. The value of the Boltzmann constant is also given in the question, which is 1.38 into 10 to the power minus 23 joules per Kelvin. Now this is the well-known Boltzmann constant and should always be remembered because this is widely used in many questions. Here the spread of molecules is given with respect to speed. We can see that 10% molecules have speed 200 meters per second, 20% molecules have speed 400 meters per second, 40% molecules have speed 600 meters per second, 20% of molecules have speed 800 meters per second, and only 10% of molecules have speed 1000 meters per second. So right hand side, the sum of the column is 100%. So first of all, let us calculate C square RMS. It means we have to calculate the number of molecules into the speed first. So this is 10 into 200 square plus 20 into 400 square plus 40 into 600 square plus 20 into 800 square plus 10 into 1000 square divided by 100. So CRMS, using the above expression, we get 639 meters per second. Further, the general expression is half MC RMS square is equal to 3 by 2 kT. Now if you remember, in my last lecture I had discussed the principle of equipartition of energy, and 3 by 2 kT represents the kinetic energy associated with the gas molecule using classical expressions. So what do we have after simplifying this? T is equal to 1 by 3 into K MC RMS square. K is the Boltzmann constant, M is the mass of a single gas molecule, C RMS has been calculated just above. Substituting the value of the following, we get temperature as 296 Kelvin. Now let us move on to the second part. C RMS square is now again calculated, which is equal to 10 into 200 square plus 20 into 400 square plus 40 into 600 square plus 20 into 800 square divided by, not 100 now, divided by 90. So C RMS now becomes 584 meters per second. Again using the general expression, half MC RMS square is equal to 3 by 2 kT. We get the new temperature as 248 Kelvin. So this is as far as the Maxwell's law of distribution is concerned. We have calculated, we have seen how the expression varies, how we can calculate the constants, how we can calculate the various kind of speeds associated with the gas molecule. So I hope students, you have understood this, and enjoyed the lecture. Thank you.